Thank you for coming. And today I'll be talking about my research on building secure, private, and transparent digital identity at scale. And here's a quick overview. I'll start with an introduction. What do I even mean by identity in this digital setting? And what is my ideal solution? Then I'll talk about what I think are the barriers to getting deployment for secure, private, transparent solutions. And an overview of my work and how it gives it works towards this ideal. So, okay, what counts as identity? Identity is an actionable binding. So you have some principles. So this could be, for example, holding a ticket for a concert. And the principle has some attributes, and it uses it. These attributes are used to authorize or deny some actions. So attributes could be, here's a ticket, it's valid for a single entry. And what is the action? I'm allowed to enter the venue. And I can have this as a QR code on my phone as well, right? Or Reddit accounts where the principle is the account itself. The attributes are karma, reputation, that kind of stuff. And the action is whether you can post or you can moderate some group or whether you can surpass some rate limits and stuff like that. So this has become a bit clearer as we go through the talk, but just as a high level overview, that's how I think of identity. By the way, it shows up everywhere. People overload the word to mean everything. You could talk about verifiable credentials and people call that identity as well. And then other people call passports identity. And the European RFC chip version makes it digital. So this is just how I like to organize the space. And then the ideal properties, I think, for an identity are security. So you want to prevent unauthorized action. So for example, for this concert ticket example, I should have paid for one ticket to be able to go inside. Two different people should not be able to copy the same QR code and go in. Then privacy is, so I'm also obviously important. Ideally, you give as little information as possible. So I'm at the door. They don't need to learn my personal information to let me in. So that would be the privacy aspect. And same, by the way, goes for when I actually buy the ticket. You need to learn as little as possible. But then at the same time, you have this tension with what I call accountability. So misbehavior is detectable. So for example, if there's somebody who's been using Ticketmaster, going to concerts, and is a known sexual harasser at these concerts and is just creating a bad ruckus, they're known miscreant, you should try to keep them out, right? And it would be nice if you could ban people like that. So that's what accountability means, and obviously it's hard with privacy. And by the way, all of this to work has to scale appropriately for whatever application you're looking at. So my overarching research hypothesis is that what is the barrier to this type of secure, private, and accountable identity in the real world? Sometimes it's new primitives, yes, but more often there are good designs in the literature, but they fail to make it to the real world because either they don't model the real world correctly, or maybe they don't design for the scale that they're going for and what requirements it starts to impose. So let me give you two examples of this in a second, but so for the realistic threat models, this would be, for example, that people are suddenly going to start behaving very differently and users will manage keys very well. That seems like an assumption that is maybe not very good to make, but we'll talk about that in a second. And for designing for scale, this would be, for example, you can't assume that you can just run your system in RAM on one server somewhere, which even I'm guilty of as a researcher. And this is great for the lab setting and it's good for comparing, but it's not necessarily going to make it to deployment. So just to give some examples of this realistic threat model line. So tick end-to-end encrypted messaging, huge success in cryptography, been deployed everywhere. Alice and Bob look up each other's public keys. The server gives it to them. So you're using something like WhatsApp, them each other's corresponding public keys. They run some sort of double ratchet fancy cryptography signal protocol, and now they're sending encrypted messages that the server can't even read. But this server is actually also an identity provider, and it could return malicious public keys, right? So the public key is this identity, and the attribute is this is valid key for this account. And this is not true necessarily. And in this way, the server could mount a meddler in the middle attack. And what's even worse, it could do it undetected. So what does this have to do with assumptions? So remember, the thread model is the server holds this dictionary mapping public keys, valid public keys for account. And it may cheat by showing different views to different parties. So Alice thinks her key is PK Alice. Bob thinks it's this PK malicious. That is a diverging view. Ideally, we want to prevent the server from cheating at all. And there have been solutions that are on paper pretty nice and have found some use that try to do this. One example was Keybase. This is actually deployed at last count is 250,000 users, pretty good. What it required you to do is you publicly posted to all of these accounts or something like this. By the way, these are all from, I'll credit their documentation. But if you notice, what accounts are these? Okay, you publicly post to Twitter that I joined the system. You post maybe to Reddit, Hacker News. Okay, well, all of these are well and good, but they're clearly kind of made for experts. I mean, the regular user isn't going to do this. And by the way, there's no stats for Keybase after 2019 because they got acquired by Zoom because they do have a fantastic cryptography team. But anyway, so there's not been a lot of dev, but I believe that this was the barrier to adoption, just all of the things that you had to do as a regular user. So the assumption was that regular users are going to be able to do all of this. Another alternative for the same problem, you can scan your QR code. This is from WhatsApp, by the way, and Yanis, thanks for letting me use this. You could either scan the QR code when you meet with your friends. You could, if you don't even trust the QR code scanning, you could say, okay, well, let's compare this manually. And the nice thing is it will prevent cheating upfront because you only message after you do this exchange. But remember, I mean, this public key cryptography, the whole point was you don't want to meet in person. And secondly, it doesn't really scale well to groups, especially ones which are dynamic and spread across the world. Maybe you could say, oh, for this group of friends, we go to a party and we're going to do this QR code exchange. I don't know what kind of nerds your friends are, but if you go to a regular party, they will not invite you back. So basically, ideally, we want to prevent cheating at all. And there were solutions that assumed that you could do this, but they required users to do stuff. Store secrets, meet in person. Sometimes this came at the cost of privacy. And by the way, Keybase didn't even have a recovery mechanism. So if you lost your key, you're kind of done. So this is the store secret aspect of it. And we still want to support, by the way, billions of clients. Yes, there's computer scientists and security conscious folk, people like everybody in this room, but also there's grandpa. My 97-year-old grandpa is on WhatsApp. He's not going to do some of these things, but we still want some level of security. So this is just saying that if you make these assumptions, you will not get to this scale. Then here's another example. Decentralized identity or a digital driver's license. And there's been solutions for this. So you have an issuer and users have this public key, private key pair, secret key pair. The issuer says the California DMV and it issues a license to Alice, links it to the public key. And then Alice has this license, which she can later use her secret key to get some services from, for example, a bank. And it's kind of nice. You could even just selectively reveal some things and finally get a loan. But where does this issuer come from? As far as I know, none of the DMVs are doing this at the moment, and they probably won't do this for a while. So this basically sweeps under the rug a chicken and egg problem. So it's assuming that some infrastructure will show up overnight for people, and so people will then have this ecosystem. And so this again is an assumption that forms a barrier. So this was just to give you a sense of one of these points. We'll talk more about the other in a second. But based on these being the two barriers, my work has been trying to make an effort towards overcoming these issues. So one line of work is identity for end-to-end encryption. So this is the public key problem I showed. And this, I worked on this in Seamless and Parakeet, and these these two papers are essentially working on something called key transparency, which I will explain shortly. And then another line of work is on legacy compatible decentralized identity. And I've worked on that in Deco and Candid. And through working on these various projects, I found that there's a whole bunch of underlying primitives also that could be improved. And obviously modular constructions are best. So if you work modularly, you will find that you could improve on some of the primitives. One primitive, for example, is authenticated dictionaries. And I will talk about this a little bit when we talk about future work, where I found some barriers in the literature. And then I've also worked on zero knowledge proof friendly primitives. But across this work, I've been lucky that my work has found some amount of impact. By the way, I should add that email that Ari sent us about Deco and TLS Notary. So Deco is patented and acquired by Chainlink and has inspired various industry work as well. WhatsApp has actually deployed parakeet-based architecture, and I will show you this in a second. And the code is open source, and Messenger also uses it. So this is deployed to billions of users. So I will tell you a little bit about how this key transparency scales to this billions of user solution and what the requirements for that are, and how we remove some of the assumptions. And then I'll talk a little bit about Candid, and finally I'll talk about this SOK a bit and link it to some of my future work. So that's going to be an overview of this talk. And by the way, across all of this work, I've worked on cryptographic solutions for the world we have. So not making assumptions about the world that we should have, and ideal users, which is really nice in the research setting, and it helps you make strides towards the harder case. But I work on the point where you're trying to meet users. And for this, I've worked on new models, frameworks, primitives, and I've built some systems that demonstrate practical feasibility of removing certain assumptions, for example. But I've also worked on systems that scale and are deployed to billions of users, as I mentioned. So with that, let us go to the key transparency line of work. So this is privacy preserving identity for end-to-end encryption. As a reminder, Alice and Bob want to talk to each other using something like WhatsApp. The system holds a dictionary that maps usernames and public keys. And we want to reduce trust in the server for giving this dictionary out correctly. So if this seems familiar, by the way, for some sort of encrypted communication, you need these public keys, you need public key infrastructure. Maybe you're thinking about certificate authorities for TLS. So website has a certificate or public key, and that's what this means, is that you've checked the certificate. Browsers used to rely on certificate authorities for this. But many hackers discovered that this was one of the biggest pain points in TLS security and actually exploited it. This is from a kind of scary Iranian hacker who says, is there any larger target than a CA? I think they meant on the internet. So not only are there individual hackers who are saying this, state-level adversaries have found this. So encryption on the web in general has state-level adversaries. So this is something to be concerned about, even in end-to-end encrypted messaging, especially where the attacks can be a lot more targeted. So in certificate transparency, the solution was that you essentially keep a log of all certificates added for a website, and this is a cryptographic log. And the goal is that if user sees a public key PK for alice.com, it should belong to the set of public keys that alice.com thinks it's valid, are valid for it. And by the way, there's a small assumption, terms and conditions apply. You have to look through the whole log. I will come to this in a second. But still, this has seen deployment, and it is fulfilling its purpose. These are just a few examples of breaches that have been discovered thanks to certificate transparency. So why am I working on key transparency? Okay, encrypted messaging, isn't it just the same? What are the challenges here? The first is a privacy requirement. Websites, literally, there are websites that pay money to get discovered on apps and advertise, but users may not want their data to be public, even metadata. For example, if I block somebody, say I'm running away from a domestic abuser, maybe I don't want them to know that I got a new phone and that I'm trying to run away. That's just one example where metadata even So your key changes because you got a new phone. That metadata tells you something, and that can be dangerous. And the public key itself could be sensitive information because you don't want to get spammed and stuff. Okay, then you also want efficiency. So as I mentioned a little bit earlier, to get a full picture of certificates in certificate transparency, you actually have to do something called monitoring, and that requires going through all certificates of all websites on that log, like basically from forever. And maybe you like catch up and then you have to keep up. So sometimes actually domains were hiring these like paid monitor parties to do this, to check their certificates, because it was just so cumbersome. And end-to-end encryption app users probably don't have the bandwidth to do it themselves. And they probably also aren't willing to pay. If you're used to using a free app, why would you want to pay, right?
In practice, what is this log?
It's a chronological Merkle tree. So you just like have a Merkle forest type of data structure.
So I mean, just on the internet, on the website, where is this?
Yeah, so that's a good question. So various certificate authorities now maintain these logs, and your browser is programmed to get certificates from different ones and make sure that they kind of match. Yeah.
And we can't do that for end-to-end.
Because well, if you use this, well, so ideally you would do that, right, for end-to-end encryption, but users might want to block someone, and that's the privacy requirement, right? And the way that it's actually done in practice is just very inefficient for certificate transparency. So for legacy reasons, it just continues to work that way. Yeah. So one example is I'm a user. I have somebody who's stalking me, for example. I want to block them on WhatsApp, but I also and sometimes people are trying to run away from the stalker, right? If I get a new phone because they put a phone app tracker in my app, an app that tracks my phone in my previous phone, I don't want them to know that I got a new phone.
So
that's just so in certificate transparency, this is all public information that, oh, there's a new certificate posted for such and such website. So this is a requirement that we want to avoid.
So this database will have like public key map.
So right now, the server maintains this this dictionary, right? And it only gives out data to permissioned users, presumably. So we are trusting the server for that still. But the data structure that we're going to introduce, the cryptography that we're going to introduce, it shouldn't do worse than what is already there, is the idea. And by the way, one other thing I'll mention about this metadata, because I know this in general, this motivation sounds a little bit weak, but I think throughout the history of various kinds of cryptographic construction in the last 20, 30 years, people have seen this happen repeatedly as a pattern where, oh, such and such metadata is okay to leak. And then somebody comes along like Paul Grubbs, and then they basically say, oh, actually, I can use this metadata as an oracle to find out such and such other thing. So just because we can't think of a large-scale attack on privacy based on just metadata leakage doesn't mean it doesn't exist.
Yes.
We're going to come to that. Yeah.
It's been hard to appreciate the problem.
Yeah. Yeah, I will actually explain all of that in a bit.
Maybe clarify again. When you say websites here, TLS case, does that correspond to people? This messaging?
Yeah.
Like phone?
I mean, well, phones, yeah.
So when you get a new phone,
it's getting a new certificate. So yeah, I guess it's like the phone account that you want to be associated with it. Okay, so then the problem statement, and we will go through this in a little bit more detail. is can we build a key transparency system similar to certificate transparency, but that simultaneously supports privacy, efficient client-side verification, which I will explain in a second, and global scale, so billions of users. So before I go into the technical details, I will briefly, actually maybe at the start of this section, I should have done this. I should have said you could take your phones out now if you don't have them out already, because I just want to show you a demo to demonstrate that this has actually worked, and that we have actually answered this in the affirmative. So what you can do is, and by the way, right now, key transparency stuff is happening automatically in WhatsApp in the background, similar to double ratchet, all of the signal protocol, other encryption stuff. But you can actually also see it in action, which is nice. So Parakeet, which I'm going to talk about, is what is deployed. So you can go log into your WhatsApp and pull up any chat with a particular friend. And then if you click on their name, you should get to their contact info. And then down there, it says encryption. Hopefully everybody has found it. And then if you go here, it should say something like verifying, and in a little bit, hopefully it should say that the encryption was automatically verified. So this is what you should expect. And by the way, this is also now deployed on Facebook Messenger, and this is their white paper. That's the QR code for it if you want to go verify my claims. But they're talking about this directory, which actually was the open source code for Parakeet as well. And they do mention my papers, Seamless and Parakeet. So it's exciting. We've across this work, we figured out how to answer those questions in the affirmative. So now I'll talk to you about how we do that a little bit more in a bit of technical detail. Okay, so before we go to further details, let's just make sure we are clear on the model. So users want lookups to be consistent. The identity provider is a party that we want to basically avoid trusting for serving correct public keys. But it's still going to sign up users. It's going to still authenticate them because we don't want users to store keys or be responsible for a lot of key management. And then updates to this identity provider data structure will be batched and take place in discrete time steps called epochs. So that's just the model. But we actually have one more party that we introduce called auditors, and can be anyone. It can be users, some trusted execution environment, third party, combination thereof. And the whole point of them is to ease users' computational load, and they just check some global predicates. For example, that a Merkle tree is correctly created and the hashing is done correctly, or that across 2 epochs, no records were deleted. But because this can be anyone, you don't want these global checks to leak any private information of individual users. So that's our model. I know this is a bit of a dense slide, so I can pause here for a second.
User checking.
Users should do some checking, but they're not doing signing, for example. Signing. And I'll come to this in a second when I talk about the security guarantee.
Like for example, Facebook or WhatsApp.
Yeah. So in this particular case, so we can actually all do it if we wanted to. This is all open source and they're posting stuff to GitHub and things like that as well. So individual people like us could be monitors if we wanted, but I think that's like kind of a starter, starting with the API right now. I don't think the UI is mature. So you will have to do it as an expert user, but they actually also have a contract with Cloudflare, and Cloudflare now does the auditing. Yeah.
So
Exactly. Well, they will have to do something for their own key, but that's happening now in the background, like I said. So what I just showed in the demo, that is actually already running in the background too, every so often.
that's true.
Yeah. So it is checking your own key periodically. And then when you get somebody else's key in order to do the double ratchet, it also checks that.
Just understand if it does that, but not this one, it's not secure.
Correct.
And the other way around.
Correct.
But if I do both, then I don't rely on another user doing their own vote.
Well, we'll come to this in a second. So I think this will all get a little bit clearer, this consistent thing when I come to the next slide, which is saying, well, so we saw preventing is very hard. It requires all these assumptions, but detection is not so hard. So what we want is we want anti-equivocation, meaning the server can't show different keys to different clients without getting caught by someone. So in particular, what does this look like? So Alice says so remember the server works in Epoch, so this is just to remind you that. But so Alice joins the messaging app at Epoch 1 with PK Alice as her public key. And then a couple of epochs later, she's checking her own key. Bob is looking up her key. If Bob gets PK bad from the server instead of PK Alice, either both proofs verify and they get the same value, which is PK Alice. But if they get PK bad, then Alice sees that there's some change. So she's detected that misbehavior. Or one of the cryptographic proofs will fail to verify. So one of them will detect the inconsistency. So they both have to check, which now you're like, okay, well, what do you mean they both have to check? You're right. No undetected, what we get is, the guarantee we're getting is there's no undetected divergence if Alice and Bob simultaneously check Alice's public key. What could go wrong with this? They're checking simultaneously. What this means is that Alice kind of is assumed to be online at all times and doing this check, right? So this motivates the need for what is called history checks, and we'll go into this now. So the idea is that, okay, Alice joins with her key. So now we're just working with the previous guarantee, anti-equivocation. So they both check, they should get the same value. So she joins, and then she maybe goes to the airport and takes a flight, and the server knows that she's on a flight now. So she's offline for a while. Maybe she's flying to a faculty interview. And so now server changes Alice's key to PK bad, and it knows she's not going to check now. Bob looks up Alice's key and gets PK bad in this duration. And then the server changes Alice's key back to PK Alice. So that later when Alice comes and looks herself up, she's missed all of this intermediate behavior and she thinks everything is fine. But everything is not fine, right? So we need some way of dealing with this users being offline. So what we introduced is an API, which we call history check. And by the way, this is the first time this was introduced was in my paper, Seamless. So the idea is, say there's a few events that happen and Alice has 3 different public keys that she's had over time. Right now at Epoch 2200, her current key is PK3 Alice. So if she comes now and asks for a history check, what she's going to get is this full picture. She's going to get, okay, I want a history check from Epoch 200 to 2200. Oh, from 200 to 300, your key was PK1 Alice. 300 to 1000 was PK2. 1000 to 2200 was PK3. That's the picture she's going to get, and she's going to get it with a proof, obviously. So now if Bob looks her up, this key history guarantee is saying if Bob looks her up during a time period that she's looking herself, that she's done the key history over, what Bob gets should correspond to what the key history would have dictated, essentially. So if Alice thinks at Epoch 900, her key should have been PK2 Alice, based on this history check, Bob's value should match.
Is Bob also allowed to run on Alice's key?
We don't permit it in our work because we say it's basically breaking some of the privacy guarantees. We can have some limited version of it, but yeah.
So I guess what we get is that we don't get some bad.
Either Bob will detect when he looks up because he also gets a proof, or Alice will detect it. Yeah.
So yeah, so I also have the question. Another question is, this seems to be, is this achieved if the log is appended?
We'll come to this. So I haven't talked about the log here yet, right? So we'll talk in a second about that. So I guess just bringing us back to the problem statement. Now that I've defined what Alice is or what the parties are verifying, can we build a key transparency system that simultaneously supports privacy, efficient client-side history checking, and global scale. And lookups are always going to be cheaper than history checking because it's just over less period. So that's what we're now focus on. And to solve this, our starting point is going to be a Merkle tree commitment. You've all probably seen this. This in particular is a lexicographic Merkle tree. So, excuse me, every node has a label. If you're at depth D, then the label is D bits. You traverse by looking for a particular label like you would in a binary search tree. You just read the next bit. And to commit to this particular dictionary of Alice and Bob's public keys, what you do is you pick a leaf label by hashing Alice's and Bob's usernames for each of them. And then you just put the public key as the value. So leaf nodes are either empty or their value is a public key. And then all the nodes above are hashes of the labels and values of the nodes below. Kind of standard. Hopefully everyone is familiar with this, and this refresher was enough. Now, the thing with this is that the hash functions, I mean, this is just a toy example, but normally hash function outputs have to be pretty long, which means that this tree is going to be pretty deep and just have a lot of leaves. So in order to avoid that, what we do is we just throw out leaves that are empty, and we also throw out intermediate nodes that are now kind of redundant because they only have one child, so you don't actually need the intermediate node anymore. So this is what it ends up looking like. And what you do, so this is just a, by the way, toy solution, right? So what you could do is you could distribute the root to all the users, and the lookup is just a Merkle proof. But there's two things, right? One, there's no privacy because anyone can compute hash of Alice. And the second thing is, as this evolves, if Alice updates her key, she has to keep checking whatever the latest version of the tree is. Even if you keep it append only in the sense that you just keep copies of this tree and you put them in a hash chain together, Alice will still have to retroactively look up all the previous versions. So it's linear in the number of time steps. Yeah. We're assuming the tree is public because, partially because, and this is true for the constructions as well, is because the auditors are going to check that the tree is well formed at minimum. Because the server could just make up a tree, right? It could just random weird data structure.
Okay, so certificate transparency uses
chronological.
Here it's lexicographic.
Yeah, because now, so chronological Merkle tree, if you want a full picture of a user, you have to, so chronological is just saying this public key is valid, this public key is valid, this public key is valid, and it's just saying that. This is saying what is the unique public key for Alice?
About the efficient lookup for
efficient lookup for every user. Exactly. Okay, so I guess we've seen that this doesn't give us privacy or efficient history checking.
So the lookup it changes with every update to the tree.
Yeah.
And this is done by the server. So
yeah.
That computation. The users don't need to compute this.
The server will give the proof, and I will tell you in a bit what kinds of problems show up with that. So this is astute. We will come to that. But yeah, the table and the data structure, they're both stored at the server. Server's doing all the modifications. Remember, it's tested for authorization or authentication. Okay, so then our problem statement again, no privacy, no efficient history checking so far. And I should have, by the way, spent a second at this roadmap, but so we've talked about a starting point. Let's talk about how we can add privacy, and then we'll talk about why that doesn't work and how to fix it. And then finally, once you fix privacy and history checking, what you need to actually scale. So this comes from a work called Connix from 2015, really good systems paper in Usenix security. So the idea was each user, again, same as before, each user gets their own leaf label, but instead of using a hash, you now use a verifiable random function, which is just like a hash in that it's deterministic, but the server is going to have a secret key. So it's the only party that can compute the hash, but anyone can verify it. So think of it kind of like almost like an inverse signature, right? It's like, okay, yeah, a signature without any randomness is deterministic. So that's just what the primitive is. We don't need to know anything else about it. Just these properties are all we need to know. So now the leaf is deterministic, you know where it is. So the server can't have two different leaves for Alice. There has to be one fixed one. But not everyone can compute it, only permitted users can compute it. And then you obviously use just a cryptographic commitment for the public key itself. So now you've hidden both the content and which user it's associated with. So no one can see that. But the leaf for a particular user is fixed. What does that mean? That means that now if Alice goes from PK to PK star, this metadata is visible to Bob. Even if the tree was not public, which as you asked before, what if you don't make the tree public? Bob can still see in this tiny tree, this is like very obvious that Bob's own Merkle path will leak something about where something changed. So if you know where something is and something changes in that subtree, you know with some probability that that change occurred. So that's not good cryptographic guarantee. And by the way, we call this more detailed attack, the tracing attack in our paper. I'll not go into more detail about it right now. You can look at the paper if you're interested. So yeah, so Bob can see all of this. And secondly, we still have this linear in number of epochs problem where, you know, even if you chain together the roots of all of these trees and you just have copies of the tree as the leaves mutate, Alice would still have to do linear work to do history checking. So again, we don't get privacy or efficient, specifically history checking.
Where you have
it's just a single tree and you just have many copies of that tree. And each copy, the root is just hashed into the next copy.
Yeah, so it's a growing, you're saying the tree grows.
There's only one tree. Rather, okay, it's only one tree. It doesn't grow with the number of versions, it grows with the number of users, so how many leaves you have. But you have many copies of it. So that you can show, oh, at epoch 5, this is what the tree looked like. At epoch 10, this is what it looked like. So that I can do retroactive checks. So that's what I mean. If either Alice is always online, in which case she's looking at the most present copy. But if you want to support Alice going offline, you need to support the copies that she missed.
So you're saying that it's
when anyone updates something. Exactly. All of the versions of her key, basically. Yeah, it's just mutating, right? It's just mutating them. Oh yeah, so this depends on the way you implement it. It's kind of a choice, but we just restrict it to one for the model. I believe in the actual WhatsApp implementation now, they do support multiple updates, but I should ask about that. Thank you.
Sorry, what was the privacy guarantee in police?
It's that you don't know what's in the node. But
Previously, why did you know? It was just a public.
It was just the public key and you know where it's hashed in. So even if you hash the public key, would still leak metadata before. Now it's you don't know what location she's at. But what I'm saying is that it's not good enough because it's still leaking metadata. Okay. So how do we fix these problems? This brings me to my work seamless. So the solution is that you still keep a Merkle tree, but now you have a new deterministic node per version of Alice's key, which means there's no longer a fixed leaf per user. You still use the VRF, by the way. So for every version, the leaf will be fixed, but each version is only entered once, and then that version number keeps incrementing. So what you do is now you hide both things. So for example, Alice's key is at version 1 and it's PK Alice. Then she updates it to version 2. I use italics too for the version number. Then a new leaf is added. So if at version 1, Alice hadn't blocked Bob and then she did block him, Bob will not know what this new leaf that's inserted is. It could be any user, right?
The story about why does it have to do with
So what I'm saying is, okay, well, you said why is the VRF not enough?
I think that example. Why does what's blocking? Yeah. What are we talking about?
So, okay, so if I didn't have block to support blocking, right, of users that already know where I am, then the conic solution is enough, because if it's leaking metadata for this particular user and you don't, it's kind of pseudonymous essentially, right, for everybody else, the conic solution, because they can't compute the hash.
So
Exactly. If you're never friends with Alice, you don't know where she is. But if you become friends with her, you will always know where she is. So the question is, what if you were friends with her and now she blocks you? I should explain that better. Okay, that's good to know. That's something.
So why does Bob know where Eddie is?
Because Bob is allowed to look her up, so the server will tell Bob.
The server will tell Bob the VRF.
Exactly. And then and Bob can verify with the VRF public key. Exactly. And then now we're saying, okay, no, actually just insert a new leaf. So now these changes are not visible to Bob. And the other thing that we will enforce is what we call the append-only property, meaning no record gets modified or deleted. And this will become useful because now we're going to talk about history checking as well. Hopefully this. Correct. Yeah. So it's as many updates as she did. So now the thing is, if we have this append-only property, Alice can remain offline for arbitrarily long, because if the server did the attack that I showed earlier, where it adds this PK bad and then takes it out, each update is going to either lead to a change in an existing node, which the auditors will detect, or it's going to be a different version. And Alice can see which versions are there for her. So now to get a timeline for like when all the changes took place, she can just look up the proofs for before and after a claimed insertion happened. And then how can the server cheat with Alice at version 2 when Bob looks her up? The server could either give as version 1, right? So we patch that by saying Bob has to check for non-membership of version 2 when he gets version 1. So that wouldn't be possible in case the version 2 exists, because that's deterministic. Then there are a couple of other subtleties. What if the server gives version 4 instead of 2? What if the server gives version 500 instead of 2? These are kind of a little bit different too, right? Because it's like, okay, now do you have to check for all the epochs the server has been through to make sure that that version number is not there? So we actually have some subtlety about how to avoid it, and it's very efficient. It's just a couple of more membership, non-membership type tests. But now history checking will be logarithmic in the number of time steps. That's what we're going to end up with. I should put that on the slide. But not just that, it's also practically efficient. Here's a diagram from the paper. The upper line is conics. This is over 1 million epochs. And just to give you contrast, you can see how far up conics is, and meanwhile seamless is at 1.1 MB even after this many epochs. So okay, so now actually we can do these two things, right? So now what about the scaling? I'm going to give you a little bit about the algorithmic improvements to scale. So here are some of the issues that come up when you try to scale. First, if you want to make statements about these past states, so remember Alice has to check when something was inserted exactly, then you do need to store them in some sort of persistent data structure. And there are many ways of doing this wrong. And you end up with very high storage and latency. Then the data structures themselves, these trees and stuff, you can't just have them in RAM or just on a machine with naive switching. between RAM and disk. So you actually need something more clever than that. Then there's this forever append only requirement that I mentioned. This is also hard to justify for two reasons. One is GDPR, which is after a certain amount of time, if a user has been inactive, you need to be able to delete their data. And secondly, try convincing, as an intern at Meta, as I was, try convincing somebody higher up to let you have resources to deploy something that you have no plan to delete anything ever. They will probably tell you no, and if you insist too much, they will probably not give you a return offer. So, so that's just an overview of some of the problems. You can look at them in the paper for more details, and some of the other issues that also come up. I'll talk a little bit about these persistent data structures. Since we've looked at trees so far, let's keep looking at trees. So in Connix, in order to support history, so Alice goes offline and she wants to check past states. What they needed to do, and I figured this out because I ran their Java code, and in trying to compare Seamless and Connix really well, I tried to implement everything apples to apples. And they just had copies of the tree. And in Java, actually, the heap fills up and the garbage collection basically just stalls everything. So you can't even do updates or anything after a while. So this was just bad for many reasons. And obviously, there's a lot of redundancy, right? Only one leaf in the tree has changed. Why are we storing all of this extra redundant copies of the same other leaf, the 1 leaf, right? So in Seamless, we figured out that, okay, well, this is going to be a big problem. So let's store the states in a way that is much more efficient. So what we said is, okay, let's just, now this tree data structure, instead of just having the values, so it has the labels, but instead of just having the values, every node is going to have its own mini dictionary inside of it. And that dictionary is going to store all of the state changes that took place. So for example, at epoch 1, if Alice and Bob were both at version 1, so that was the epoch 1 version of the tree that we saw before. At epoch 2, Alice inserted version 2. This node, this is how insertion in these compressed trees works. This node was only created at timestamp 2. So we need to also keep track of subtlety if we want to look back where the node that was here previously went. But all of this is a little bit subtle. You should check out the paper if this is of interest, or not, because we actually figured out that this was also too cumbersome storage-wise when we worked on Parakeet. Once you get to billions of users, it's still untenable to store all the different states. So what we realized is if you hash in to each leaf when the leaf was created, then you don't need to look at past states. The current state can tell you when it was created exactly. And the audit and even though the commitment is hiding, this epoch of insertion is public anyway to the auditors at least. So the auditors can check when this insertion happened. So they can make sure that the correct epoch is hashed in. So now you can just look at this current version of the tree and you can be able to see like, oh, which epoch was this node inserted in? But if I do want some older versions to take out, and that actually there's subtleties and reasons why you might want that. For example, like checkpointing and versioning, just in case you're for fault tolerance. We no longer actually there's some subtlety in metadata you have to store, but there's not a lot. And again, we end up with pretty concrete benefits. This is Seamless versus Parakeet over 5 years with 10 million users a day, which is updating 10 million updates a day, which is pretty plausible for WhatsApp scale. And as you can see, it's more than 110 terabytes for Seamless, and so this is terabytes, and for Parakeet it's less than 3.4. So yeah, so the benefit was tangible. Yeah, I did not really get paid for the storage. I helped them save with this, but I guess I get bragging rights for this talk. But we did manage to get all of these things. Now, privacy, efficient client-side history checking, and global scale. And by the way, I mentioned some of these issues. There's some solutions to this. What I want to point out is that each of these solutions required a different style of contribution for my work. So the data structure stuff that we just saw requires cryptographic data structure algorithm type improvements. State machine replication, so having some outsourced storage actually requires some system design, evaluation, and optimization, because actually there's lower bounds there, so it has to be concrete improvements. And the append-only assumption that I removed, that requires some cryptographic modeling for the real world. Okay, I think I'm like way over time, so I'm gonna skip this candid part now. I'll just go to the future work. But just as a quick overview, so Parakeet, by the way, is a complete solution. I've just talked about this commitment part, but Parakeet also talks about how users can access this commitment in a sort of trustworthy or more trustworthy way than just getting it from the server. And that's all in the paper, and it's very lightweight actually. Okay, so there's this decentralized identity section. We're not gonna go over this. Yada yada yada. Okay, a whole lot of slides here. Okay. Okay, so finally, I'd like to talk a little bit about ongoing and future work. I promise I'm almost done. And as part of this, I'll talk about what my common research approach is, and try to convince you that this identity thing is a pretty rich problem space, and that the underlying primitives are also interesting, and also would be interesting avenues for collaboration with all of you. So the common research approach is reducing trust while being realistic. So in key transparency, we did this by removing trust in the identity provider, but also not requiring assumptions of users. And in identity bootstrapping, we reduced trust in a single source to do out-of-band checks, as well as providing cryptographic ID. We worked within existing ecosystems, and that yields pretty interesting constraints. And these interesting constraints, along with storage, well, various kinds of scaling requirements, end up with needing very interesting technical solutions. So in future work, I would like to work on privacy preserving identity for the AI age. We all know we're here. And in particular, everybody knows AI is coming for our social media, and it's going to be pretty much useless if we get a lot of AI slop. So we would like some sort of way to mark humans versus AI for social media. And you might ask, is candid plus some sort of verifiable credential solution enough for this? But no, because we're trying to also mitigate users selling their identity. So by the way, there is evidence that people are already doing this. Roblox is a video game system. Maybe some of you who have teenagers in your house have heard about it. But there were a lot of sexual predators, child sexual predators, going on Roblox and trying to groom children. And it was pretty bad. So they tried to fix it by having this ID solution where children and adults have to basically do like video verification to get an ID. It's like a kid ID and an adult ID, and you don't talk to each other essentially. But there's already a black market for these kid IDs for these groomers who want to go on. So it's pretty messed up, right? So this is just an example. So how could we solve this? One example is if I immediately can revoke and refresh an ID as soon as I sell it, then it's kind of worthless to buy. But it introduces some other issues. A person could be using their ID as a front for like their whole swarm of AI agents. What about this revocation flow? How do you do it in a way that doesn't make it an attack vector? There's a whole bunch of interesting questions here. But more generally, to map the space, I think of a life cycle for identity where things often go wrong. There's the establish phase where you bind an identity to attributes. Maintain, where you ensure that this binding remains correct. And use, where you prove ownership or authorize use for particular attributes. And by the way, the messaging thing that we have looked at kind of fits in here. And so does, for example, using single sign-on for work. So it's a pretty rich problem set. Just to give you a few examples. So this has to do with anonymous and verifiable credentials. So can we plug in some of the solutions I've mentioned with anonymous and verifiable credentials? Use could actually also feed into establish, because you could use reputation as a way to get more attributes for your identity. Maintain could have to do with delegation with global properties, like I'm delegating my account to this AI agent, but it can't spend more than $300 a day, for instance, those kinds of stopgaps. So So there's all kinds of stuff to be done here. And I would like to look at different scenarios that maybe seem the same on the surface, but some additional requirements make them much more challenging and to require different technical solutions. And by the way, obviously cryptographic tools as a cryptographer are very interesting to me. So one example is the underlying primitive authenticated dictionary for parakeet. It works really well. It works in practice, as we've seen. It was pretty fast. Everybody, I think, was able to do the demo in the 1 minute that I allotted for it. But what about asymptotics? Both updates and lookups are log n for parakeet. Is this true across the literature? I tried to answer this question in this SOK that is going to appear in NESS in a few weeks. And you don't need to worry about this table. This is just to show you we looked at a whole lot of papers with different threat models as well, but with the same primitive. And what we found is across different kinds of solutions, you only had log n for both lookups and updates, or O of 1 and O of n for lookups and updates, or vice versa. Or one of the operations, which is worse. And this holds for constructions that are amortized, holds for constructions with different trust models. So then the question is there a lower bound? I've been working towards that. And that includes reductions to related primitives, things like that. And by the way, I would love to use some of the stuff that we find for authenticated dictionaries to build databases that are verifiable as well, that actually perform like the load balanced databases that we use right now with caching and stuff like that. And I've been lucky to have some impact and some recognition. The repository that I showed you earlier, that was cited in the key transparency WhatsApp. This is a screenshot from that repository from a few days ago. I'm still the 4th highest contributor. There's a team of engineers working on it, which is really exciting, but I'm very proud to have contributed enough to still be a pretty high contributor. And there's also a key transparency working group. Not sure if, I think there people will be familiar with the IETF process, but the standardization process, but you start with a birds of a feather to sort of see if there's enough there for a working group. And I was at the birds of a feather presenting, trying to make the argument that we should look into this seriously. And it won the Applied Networking Research Prize. DECO's been patented, acquired by Chainlink Labs. And I would like to thank all of my collaborators who are all really awesome. And there's many more. And as you can see, I've worked with people in industry and academia, somewhere in between. Jens is both at UCL and at Nexus. And both very senior people. Don Beaver is semi-retired right now, but also had a lot of really good mentees. So with that, I would like to thank you, and thanks for coming to my talk.